Log on, tune in, find out. Another good idea from Cambridge.
From Polytechnique, we'll talk about sampling methods for time domain inverse scattering problems. Please.
Thank you, Mika. I would also like to thank the organizers of the workshop, the Institute, for this nice workshop. It's a pleasure to be here, and I'm honored to speak here. As you've seen from the title of the talk, this talk is something like a dessert to Andreas' talk from yesterday.
Microphone's not on.
Microphone off, I'm sorry. Microphone's on. So this talk is kind of a dessert to Andreas' talk from yesterday, who was also on the factorization method, and I'll recycle quite a lot of the structure he already introduced to you in kind of a different context. So Andreas was working in the frequency domain, and I'm really going to work in the time domain. So the problem I will look at is the following. Imagine you have a bunch of source-receiver pairs, and some of these sources emit waves in the time domain that start at some initial time and then propagate. And then there's some scatterers out there. These scattered waves at some moment will reach these scatterers. They will scatter away from the scatterers, and then the receivers measure the scattered fields. So it's a time domain scattering problem, and the aim is, of course, from the scattering data to reconstruct the scatterers. Now, this is somehow a personal preference of myself. I will use these sampling methods to solve this problem in a kind of similar way that was already introduced to you yesterday and the week before by Andreas, by Fiora, by David. So what are these methods? This is just a reminder from yesterday. So somehow the characteristic feature of all these methods is that they start by giving up something, really. You give up the aim to reconstruct everything. Namely, you are not interested anymore in reconstructing physical properties of the material. You're not interested in values of the material parameters, but you're just interested in shape. That's all you want. You give up to aim to reconstruct everything. What you gain, on the other hand, is very fast methods to do this support reconstruction. And I guess all these sampling methods that are around nowadays have this feature that they are non-iterative, they are direct, they are fast, and they do this support reconstruction. This story started by this linear sampling method. Fiora told you about that yesterday. And the field was quite rapidly growing, and there are a couple of distinguished persons among us who contributed. So I concentrate on the linear sampling method and on the factorization method, and I do a final remark on that slide. So both methods are imaging techniques. So what you get in the end is a picture. I guess that's good to have in mind. The method gives you a picture, really, and what you do with that picture afterwards, that's up to you. But the method really gives you a picture, and to do that, it requires pretty good data. It requires multistatic data. If you feed in good data into the method, you get back pretty good reconstructions. Still, you need to feed in this multistatic data. And what is really great is that for both techniques, you really don't need a priori information. You don't need to know how many connected components your scatterer has. You don't need to know what boundary conditions or what kind of transmission conditions on the boundary of the scatterers are present. So how does it work? Andreas already introduced that yesterday too. So the method gives you sort of a pointwise criterion whether a point is inside or outside. Remember yesterday there was this Picard criterion popping up in Andreas' talk. This is what I mean here. So in order to get that picture, you would then cover your domain of interest with a sampling grid and evaluate that criteria on that grid, and pictures that you get from the method look like that. I guess that's with no artificial noise, and you can guess what the scatterer is, and that's with, I guess, 5% noise. Well, so people looked at that, and then there's a recent development in this theory that is sometimes at least you are not only have access to one frequency data, to data from a fixed frequency, but actually to a bunch of frequencies, to several. So why not try to use several frequencies to improve the reconstruction of the stability? And then the first idea, of course, that one has is that, okay, let's try to do these reconstructions at a bunch of frequency. Then you get a bunch of pictures, and you try to compute out, to synthesize out of these pictures a new picture which is better. You can do that. The problem, of course, that appears is what to do if you have reconstructions at a bunch of frequencies, and how to re-get a final result. There's also an issue about regularization if you work at multiple frequency, and there's also this issue about exceptional frequencies. Fiora explained yesterday to you that the linear sampling method fails at these transmission eigenvalues. So if by some bad luck one of these frequencies where you have data is an exceptional one, then at that frequency it might fail, and then the final result might not be good. Anyway, that's all to motivate to give up or to not to do this multi-frequency thing in this talk, but really to work on the other side of the Fourier transform, so to say, really to work on the time domain data directly. So there are cases where you have time domain data. Why not doing inverse problems directly in the time domain without going into the Fourier domain, without taking lots of Fourier transforms, but directly treat time domain data in the time domain. So how does the data look like? Well, pretty simple. So imagine that this yellow piece here is a scatterer, and that these three dots here are sources or receivers. Imagine that one of them sends in a wave, and then all three measure the scattered wave. So the black one might record something like that curve, the blue one something like that curve, and the red one might record that curve, and that would be the data. That's not yet multistatic, but that's how the data would look like. And from the data, the aim is now to construct such a sampling method. The data is hence causal solutions to the wave equation measured at points or at boundaries. The hope is somehow that you get better reconstruction, since you use actually a continuum of frequencies. The hope is somehow also that you can significantly reduce the number of measurement points you need. And what is nice about all that is that things like regularization becomes pretty natural, because you're regularizing directly in the time domain, and you don't end up with a bunch of pictures at each frequency that you need to synthesize afterwards. There's related work, of course. Many people have looked at scattering in the time domain, at inverse problems for time domain scattering. So there's this multi-frequency linear sampling method that recently popped up. Roland has worked quite a lot on sampling methods in the time domain, I guess for the probe method and the point source method. There's a very nice there are very nice developments on ideas connected to time reversal and boundary control, with very nice recent papers. All what I'm mentioning here is say for wave equations where the background parameters looks kind of reasonable. If you go to media that are cluttered, things are much more complicated, and since I'm really not the expert, I'm looking forward to Prisula's talk tomorrow. You see that the work I'm citing is strongly biased towards the conference participants. On the other hand, that shows that inverse problems for wave scattering is quite an interesting issue also at this workshop. Okay, so that was kind of the introduction. Now, what do we try to do? I'll first have a look at an inverse scattering problem with near-field data where you measure fields at finite distances to the scatterer, because that's somehow more intuitive, I guess. And then in the second part of the talk, I'll move to this far-field inverse scattering in the time domain, which has a bit more mathematical structure, where you can prove more things. So in the near-field regime, what's happening? Well, we have a scatterer that is called D in the entire talk. The hypothesis on D, or the assumptions on D, are that they are as in Andreas' talk. So D is an object that might have multiple components, but the complement of D needs to be connected. So D has no holes, as in Andreas' talk. And then there's sort of a measurement surface that I call gamma. There are receivers and emitters on this gamma. So for points on x0 on gamma, we look at point sources, at incident point sources. Those scatter at D, and we collect the scattered fields on gamma. What are these point sources, and what are the scattered fields? Well, the point sources, they come from the fundamental solution of the wave equation that is convolved by some smooth, let's say, pulse shape that I call chi in the entire talk. Chi is a causal function, then also the convolution is a causal function. You see that this incident point source is smooth in time, but it's singular in space. And then the scattered field that I call US, which depends on x and t, and implicitly also on the parameter x0 that comes from the incident field. It's also a wave equation with a Dirichlet boundary condition on the obstacle, and US is also causal. The inverse problem is then given measurements of these causal waves for, say, all points x0 on this surface gamma, and also all x on gamma, and also, say, all t in R, find D. And it's of course a horribly overdetermined problem, but for this talk I won't care. The idea is that sometimes you have that data, so why not using it? The idea of this linear sampling method is then to look at integral operators, at linear integral operators that are generated from the data. So using these scattered fields, you build up an integral operator by convolution in time and weighting in space. So you do linear combination with such a density, and then the idea is to show something that looks, roughly speaking, like that. So for a sampling point in space, you check whether the point source at this sampling point belongs to the range of that operator or not. So the picture I will show you on the next slide is obtained from plotting 1 over the norm of GZ, where GZ is an approximate solution to this near-field equation. And the pictures look like that. So on the left, this is something that is computed using time domain data by what I showed on the last slide. What is on the right is a standard LSM in the frequency domain, what you've seen yesterday essentially. The pulse in the time domain has a certain central frequency, which is about 1.6, and the frequency domain reconstruction is at the central frequency. These blue dots indicate where the sources receivers are. You see there are many more in the frequency domain reconstruction than in the time domain reconstruction. And what the significance of this example is that it shows to you that the frequency domain reconstruction might have problems if the obstacles, so here are two obstacles indicated by these black lines, if they are such that there appears a sort of resonance between them that is just due to the distance, which is about half the wavelength. And if the wavelength in the frequency domain is just about, well, twice that distance, then the method, there appears sort of a phantom in between that is wrong. So there's an artifact, and you see that the time domain version does not suffer from this disadvantage. So the message here is the time domain version gives you better reconstructions, or it makes sense whenever the frequency domain version does not give good reconstructions. Of course, if already the frequency domain reconstructions gives good results, then probably the time domain version will have difficulties to beat that. Whenever the frequency domain version fails, then the time domain version might really help. Another advantage I mentioned already of the method is that it's fairly independent of the boundary conditions at the scatterers, so you can do this not only with Dirichlet conditions but also with Neumann or say Robin boundary conditions. In that reconstruction, so there is one object which has a Neumann condition and one with a Dirichlet condition. Of course, these are not known in advance, and the method, I guess, pretty reasonably finds shapes. About the analysis of this near field linear sampling method, so this analysis is based on integral equations. That's not very surprising given the fact that in the time harmonic regime, integral equations play a pretty important role for inverse scattering theory. I guess in the time domain it's very convenient to use the same tools. So there pop up potentials. They are now retarded potentials since we are in the time domain. So here's the retarded single layer potential in the time domain. So it takes a density phi, which lives on the boundary of the object, and has also a time variable. So the first variable is space, second is time. This is the retarded potential in time. I call that U on that slide. So the potential is evaluated for points x outside the scatterer in the complement of the scattering object. If you restrict that function to the boundary of the object, you get back the retarded single layer operator. If you know how things work in the frequency domain, it's precisely the same. The importance about this function U is that it solves the wave equation in the exterior of the scatterer, so in the exterior of D, and it takes boundary values that equal S phi, so the single layer operator applied to phi. So at least formally, if you want to solve boundary value problems for the wave equation, then you can try to represent your solution as a single layer operator, as a single layer potential with a certain density phi, and all you need to solve if this U has to satisfy boundary values, well then the phi has to satisfy a retarded boundary integral equation. And well, how to analyze these integral equations? Well, there's a very nice theory on that goes back to Bamberger and Taduan in the 80s, who use Laplace transform techniques. Their idea was, okay, I have this problem, the time domain, and in order to analyze this boundary integral equation, well, it would be nice to prove sort of coercivity of the integral operators. That's how you would usually proceed. Now, if you have the idea to go to the Fourier domain, and you first can try to take a Fourier transform, then you end up with lots of Fourier transform problems that depend on the wave number k that is real. And unfortunately, the Helmholtz equation is not coercive because the Laplacian has a different sign compared to the k square u. So you need to estimate lots of non-coercive problems. That's a bit tedious, not so easy to do. It's much easier if you don't use a Fourier transform on the real line, but you shift that slightly into the complex plane using a Fourier Laplace transform at wave number s, or at frequency s, such that the imaginary part equals sigma, which is positive. Because then all these Helmholtz problems that pop up after taking the transform, they are coercive because the wave number is complex. At complex wave number you can estimate. The estimates actually will only depend on sigma, so they will be uniform in sigma, and that's why you can go back to the time domain afterwards. This basis that you end up with finally, if you do these Fourier Laplace transform techniques for boundary integral equations, are typically like that beast here. So it's Sobolev spaces that contain exponential weights. So e to the minus sigma t appears as a weight on the function in time, and m is the Sobolev regularity. So if sigma is 0, then you get more or less the usual Sobolev spaces hm, say. But now there's this exponential weight in time that comes from the Laplace transform. And what you can show, for instance, is that the single layer operator is bounded from W sigma p to W sigma p minus 1 in time. In space, it's as it has to be. Unfortunately, or interestingly, the inverse to the single layer operator maps also, well, if you look at it in W sigma p, it is bounded into W sigma p minus 2. So you lose derivatives for S if you look at S, and you also lose derivatives if you look at its inverse, which is kind of surprising. Still, the result is correct, and nothing better than that has been proven. The reason is just that all the techniques relies on these bounds that you get in the Laplace domain, and there you always have to pay in sigma. That's why you always lose powers of why you always lose in regularity. Anyway, that's not such a big problem. What is nice and what I should mention is that you have even a sort of coercivity of this inverse of the single layer if you look at it in these weighted spaces that contain exponential weights. That will actually be quite important for the sequel of the talk. So the single layer, well, the inverse of the single layer operator has certain positivity properties, say. Now in the frequency domain, it's quite standard that if you measure your scattered wave, say 3-4 wavelengths away from the scattering object, then the data you receive already looks very much like the asymptotic expansion of the wave at infinity, so you're almost measuring the far field already. So if you're far enough away from the scattering object, it's reasonable to use these far field measurements as a model. Similar things can be done in the time domain, and I briefly motivate why I look at that, because it might seem very weird if you don't know this notion of far fields. Well, this far field data that I'll explain in the next slide is in a certain sense better because there's more mathematical structure. Due to the structure, you can prove more than you can prove in the near field regime. More is you can do this factorization game in the far field regime. In the near field regime, that's just not possible because you don't have the structure you need. What is that structure? Well, Andreas told you yesterday, I recall. So to do this factorization thing, you need to have a factorization of your data operator that I call S now in form of such a, say, self-adjoint factorization where H star and H appear. That's quite essential. What you also need is a characterization of the obstacle using this operator H star using special test functions. Looks a bit weird in the beginning, but that's actually that's the easy part really. I've never seen any problem for that. Second point, what is much more stringent is that this middle operator T has to satisfy a certain positivity properties that appeared in Andreas' talk yesterday. This positivity of T that you need, this is sometimes difficult to prove. It is sometimes simply wrong. And in those cases, you can't apply the method, at least not rigorously. And it is usually restrictive. In Andreas' talk yesterday, you saw for these medium scattering problems, there appear these conditions on the contrast, that the contrast Q has to be either positive or negative, but is not allowed to change sign. This is what I mean by restrictive. Okay, and the final remark, Andreas told you yesterday that this factorization method uses square roots of the measurement operator. You characterize obstacles by looking at the square root of this f here, and this square root is of course a nonlinear operation, which implies that this time domain version of the method is not relied to the frequency domain version, at least not by simple transformation. So the results in the frequency domain don't really help you in the time domain, and the results in the time domain imply nothing for the frequency domain because there is no linear relation between the methods due to this square root that appears. Okay, so what's the method? What's the model? So we look at wave propagation using incident wave fronts, which look like that. those illuminate the scatterer. There's a scattered field that is defined as in the near field. Now the only difference is that I look at far field data of the scattered wave, which is you look at the scattered wave on a certain ray defined by a vector psi on the unit sphere. And if you look at the scattered wave on that ray for a large distance away from the object at time t plus r, and you rescale the wave by r because it decays, then you see that this expression has a limit. It's called the far field, and the far field depends then on direction and on time. If you know what the far field is in the frequency domain, then you might ask what is the relation, and the message of that slide is that the relation is Fourier transform. So if you formally apply Fourier transforms to that relation between the scattered field and the far field pattern, then you find exactly what you know from the frequency domain. So if you're an expert on frequency domain scattering, then think of this far field in the time domain as an inverse Fourier transform. But note that of course it is not defined via Fourier transforms, but it's naturally set in the time domain. A similar thing happens if you look at layer potentials. So if you look at a single layer potential, then you can compute its far field pattern, and it's again an integral operator. If you Fourier transform that, you end up with exactly the expression that you know from the Fourier domain. So it's not new, it's just different. A different way of looking at things. Now here's the setting I'd like to look at. So I look at incident Herglotz wave functions, which are, say, linear combinations of wave fronts with a certain direction. At that point, you should note that it was an ingenious idea of the organizers to schedule my talk together with Plummon's. You see, there's also this X-ray stuff popping up slightly, which gives probably the relation between my and Plummon's talk. I was very happy to discover that. So these Herglotz waves solve the wave equation. That's not difficult to see. And the far field operator is now defined to map G, which is that density, to the far field pattern of the scattered wave for that incident wave Vg. So that illuminates the obstacle. Then there's the scattered field, which has a far field, and F maps G to U infinity. The inverse problem is, given that F, give me the D. Formally, this can again be written as an integral operator. So if you like integral operators, you can go back to D's. I won't go into details D because this is not so important. What is more important is factorization, positivity, and characterization, and we'll try to see all these 3 points briefly on 2 slides. So to factorize, I define a Herglotz operator which just gives me the evaluation of the Herglotz wave function on the boundary of the obstacle. So it's that guy evaluated on that set. The scattered field is found by boundary integral equations. So US is a single layer potential. The phi, well, this has to satisfy a retarded boundary integral equation, which you can just write like that because the inverse to the single layer operator exists. I already showed you how to compute the far field of such a single layer potential. The far field is just this integral operator, and I'd like to abbreviate that by R for a second. Okay, what we want is the far field to that guy, which is obviously given by R applied to the density. The density solves this boundary integral equation, so you get that U infinity is R s to the minus 1 h. And at that point, we are really lucky, because it turns out that if you look at the inner product of L2 on the unit sphere and time, then R is just h star. This is just a change of variables. It's not even integration by parts, it's really just a change of variables, which shows you that you get this self-adjoint factorization for f, but pay attention, it's only self-adjoint if you look at it for the inner product of L2 on the unit sphere and time. This will cause a problem. To illustrate that, so this f is something which operates on the unit sphere and time. H is something that gives you the incident field on the structure. The inverse of the single layer is what gives you the scattered field, and H star is what gives you the far field of that. So you can decompose that into incidence, scattering, and far fields. Well, yeah, there's this thing about function spaces. Since we are doing mathematics, we want to prove theorems. Those are set in function spaces, and that's where this story gets a bit difficult. First, these exponentially weighted spaces I introduced a couple of slides ago, those are nice tools to show that you can that f is well defined on those exponentially weighted function spaces, at least on smooth functions with compact support, say. So you can sensibly define f. The problem is, of course, that this adjoint relation does only hold for this L2 inner product without weight. So if you want to use these exponentially weighted spaces, you run into trouble, because then that's wrong, and then the edge, you don't have this self-factorization, and you're out. So we are kind of forced to work somehow in L2, at least in Gelfand triples over L2 in some sense. Second thing is we need this positivity. Well, there's this Bomberger-Aduyon result, which gives you positivity, but only with exponential weights. Well, that can be solved, really. So think of psi being smooth with compact support. Then actually we can take sigma tend to 0 here, because the integral over R has really finite bounds, which gives you that. Well, of course you don't get a strict lower bound, but you get just 0 as a lower bound. Anyway, and then here I would like to integrate by parts once in order to get rid of the minus sign, which shows you then that the time derivative of the inverse of the single layer operator is positive, at least on smooth functions with compact support. So we have positivity, we have adjointness in say L2. This positivity is not a, well, is great, because if you apply the time derivative to the far field operator, then you see that dt commutes with h star. So you also get a nice self-adjoint factorization for the time derivative, where now this positive operator appears in the middle. Still, we haven't found good function spaces. The criteria to seek them is, well, we should find x and y somehow such that h is bounded between them, that this guy is bounded from y to y star, and then we would look at f from x to h star. And it took us quite a while to find good ones who do that job, because that is difficult, and that's also not obvious. What we finally took were Sobolev spaces that have a polynomial weight in time, because they have a nice interpretation under the Fourier transform, because you just exchange multiplication and differentiation. Won't go into details here. I just show you the final result. So minus the time derivative of f and the time derivative of the inverse of the single layer, they are non-negative, and that's why we can find square roots of those, which gives us two factorizations of this time derivative of f. That one, which is natural because that is positive, and that one which comes from the factorization we've shown before. Now, if you have that situation, that's pretty great. If you have two factorizations in self-adjoint form of the same operator, then you can show that the ranges of that one and that one coincide. So the range of QF star is the range of H star QS star, and QS star is almost like an isomorphism. Some sense? So you can express the range of the square root of, let's just say of f, let's omit the time derivative, in terms of the range of, well, it's almost the range of H star. And now it's the same situation as yesterday. The range of H star characterizes the obstacle via special test functions. These test functions are now far field of point sources. That's what you expect if you know the theory. And those just look like that. Which brings us back to Plummer's talk in some sense. And then I skip a lot of technical details and rather long pages of rather difficult estimates to show you the final result. So if you choose this density chi correctly, so it has to be, say, smooth enough, or it has to have a Fourier decay that is small, that is strong enough. Anyway, if you choose it correctly, then if you choose a sampling point inside D, then this function belongs to the range of this square root of dtf. If Z is outside the closure of D, then it does not, which gives you an explicit characterization of D in terms of this time domain far field operator, well, rather of its square root. Anyway, to conclude, so we looked at inverse scattering in the time domain. I hope I convinced you that there are nice structures appearing that resemble to the structures that you know from the time harmonic regime. You can do linear sampling method in the near field regime. You can't do factorization because there's not enough structure. This self-adjoint structure does not hold, it's not there. Sorry. You can do a factorization method in the far field regime because there you get back these self-adjoint structures, and then you can do this explicit characterization. What is maybe a good thing to remember from this talk is that the analysis of the method uses Fourier transforms. The algorithm itself does not. It works entirely in the time domain. Thanks.